This episode of Physical Attraction is sponsored by Podcorn. Some of you out there may be fellow podcasters, e.g. if you're in our Science Podcasts Facebook group. If so, you'll know the extraordinary amount of work that has to go into researching, writing, recording and editing your own show. If you're a small indie show like this one, getting sponsorships to make what you do even remotely sustainable can be tough. Podcorn are aiming to change that. It's a place where podcasters can go to pitch ad space on their shows to people who might want to work with them. One advantage to this is you do get to pick who you work with. I know other shows use dynamic insertion, which is done by their podcasting company, and therefore they end up filled with extremely ironic ads for people they've just criticised. This way I can filter out neoclassical economists, fossil fuel companies, any governments that I've criticised, and flat earthers, so it's all good. If you're a podcaster and you want to find out more, check out the Podcorn link in our show notes, and thanks for listening to this and helping me buy more caffeine. This week's episode is sponsored by the web and game development tutorials over on morganpage.tech. Morgan's web and game development courses can allow you to improve your coding skills and have fun at the same time. There are options to create survival games, tutorials on creating RPG card games, zombie horde type games, but even if you're not planning to code any games, you can use their site to generally brush up on your skills in coding languages like JavaScript, HTML and CSS, which form much of the backbone of the internet. There are some free courses available on morganpage.tech too, so you can get an example of what you'll be buying, but you can also get access to all of their courses for a single monthly subscription fee. What's more, you can use the coupon code PHYSICALATTRACTION to get 20% off any purchase when you go to the counter and let them know that we sent you. So if you're interested in learning a new skill or brushing up on your existing JavaScript, or indeed just coding up some games as a fun side project, that's morganpage.tech or the courses at morganpage.teachable.com. Thanks very much, on with the show. Hello and welcome to this episode of Climate 201, the third part of our series on energy efficiency, where we're going to be talking about energy efficiency in industry. In this series we've been talking about the efficiency cornucopian view, the idea that energy efficiency is really key to our efforts to reduce CO2 emissions, as represented by Amory Lovins's work from the Rocky Mountain Institute and others. We've been presenting that point of view and then many of the caveats that apply to it. And this time we'll be talking about the industrial and electricity applications and how energy efficiency can be deployed there. Typically, there are lots of sectors of industry that are generally considered to be hard to decarbonise sectors. In other words, it might be fairly easy to switch from a coal-fired power plant to a network of nuclear, solar, storage and wind and still achieve the same end result of producing the electricity you want with substantially lower CO2 emissions. This is simply because there are other ways of generating electricity that do the job just as well. Spinning turbines with heat from nuclear reactors rather than fossil fuels, or directly spinning those turbines with the wind, or else getting electricity from photovoltaic panels. In lots of industrial processes though, things like chemical reactions, smelting or whatever, you need to get to incredibly high temperatures for given chemical reactions to take place. You need to produce a lot of industrial heat. Typically, and traditionally, this has been done by burning fossil fuels. There are no two ways about it. David Roberts of Vox, who is one of the better popular climate writers out there, pointed out in an article that 10% of global CO2 emissions are from processes that produce industrial heat. 10% might not sound like a lot, but compare that to cars at 6% and planes at 2%, and suddenly you see that the problem of decarbonising heat in industry is bigger than cars and planes combined. Yet it's not something that is regularly discussed in terms of our CO2 emissions outside of climate change circles. So let's talk about some of the reasons why this is such a big problem. First off, there aren't that many customers for industrial heat. All of these deals are being done by a few big companies that are producing these goods that require them, such as chemicals and so on. In some ways this is a positive, because you don't have the same issue of convincing hundreds of millions of people to replace their boilers or cars as we've discussed in earlier episodes. You're dealing with fewer stakeholders overall. But on the other hand, it means that you can't rely on consumer choice to drive changes in the market. I think corporate responsibility is a huge area of possible future action on climate change, and it's good to see this last year that some companies are finally starting to make plans to deal with their own impact on emissions in the future. However, when we're dealing with industries that will often offshore for cheaper labour, where the margins are small and the competition is very tight, it's hard to imagine why they would switch to more expensive or untested technologies at their own expense, just for the sake of saving the planet, if they have any alternative. If you're in heavy industry, you have a lot of inertia in the plant that you're using. These are huge, costly machines that are supposed to work for decades, and so you can't constantly replace them with newer, greener models on a whim. For that to happen, you're going to need a carbon tax or regulations that are going to make the change worth your while. And we're talking about industries like cement, steel, and chemicals. These are globally traded commodities, and they have razor-thin margins on profit generally, and there's fierce competition for production. So part of the problem here, of course, is that if you in one country regulate and say you need to produce your steel in a certain way, and that steel, for example, might involve something like carbon capture and storage being appended onto the end of it, so that it is a carbon neutral process, well, unfortunately, if you can only do that in one country, then the cost of producing steel becomes more expensive as a result, and you don't make up for that, then you're going to suffer because your steel production will simply go elsewhere and it will be imported in the future. So if it is more expensive to switch to these greener heat alternatives to industrial heat, then you're going to need to subsidise the industry to make it competitive. If the industry sees these regulations as a threat to their profit margins, then the industry is going to lobby against them. And these industries tend to be exempted quite often from environmental regulations. Even in nations in the West, where environmental regulations can be quite high on the agenda, they are associated with this industrial heritage and national pride and so on. In Britain, there's some new story every few months about some expensive deal to save British steel or some other heavy manufacturing that we have here. It could be that it's just nostalgia or the perception that these jobs in heavy manufacturing can be protected and defended in a globalised world. But whatever it is, it does make it difficult for us to regulate them too harshly, politically. And of course, you think about these big industrial plants and so on, and again you look at how our political system works. If you've got this major plant that is the main employer in a region, or hoping to be the main employer in a region, then it can be difficult politically to get the people who are actually representing that region on side of something that is unpopular with the owners of the plant. They can wield quite a lot of political influence through the fact that they have quite a densely concentrated employer base. And of course, if these green measures do incur extra costs, but they aren't applied universally, then the industries may well just move to some country that's not concerned with carbon emissions. In some cases, though, the issues aren't political, and the green alternatives are simply hard to find or still in development. Take the use of coal in steel production. Coal in producing steel actually serves more purposes than just providing heat. It's not just the heat that burning it provides, but also the carbon and porosity that actually go into making the steel in the first place. It's not that easy to substitute this for a different material. There are several options here. Biomass for heat is an option, burning wood chips and so on in place of fossil fuels. In some cases, hydrogen can be used, and you can at least in theory produce hydrogen through renewable means. In some cases, electricity can be used directly as a source of heat. Even nuclear power could. And finally, if you do insist on burning fossil fuels, you can add carbon capture and storage to try and eliminate the CO2 emissions at the very least from that. Now, all of these technologies deserve their own episodes as part of a bigger climate series, so I won't go into too much depth here, but only to say that there's plenty of pros and cons in each of these different materials that you're trying to use. One thing I would point out fairly quickly is that the case for using electricity is a slightly complicated one when it comes to industrial heat. One way of thinking about it is that the electricity is this higher grade form of energy because it's more organised. The electrons carry electricity and energy in the direction that you want them to, whereas heat is molecules randomly and energetically bouncing around in all directions. So if you're converting high-grade electricity into low-grade heat, your process is going to be lossier. Consider a car engine. The useful thing you want there is motion in the wheels. In an internal combustion engine, you waste a lot of the fuel's energy as heat when it's burned. Replacing that with a more efficient electric engine, which can convert most of the high-grade energy as motion as heat, that intrinsically makes sense. But converting high-grade electricity into low-grade heat might seem wasteful, especially when we have so much kit, fossil fuel power plants, that's devoted to going the other way. If solar and wind do become incredibly dirt cheap, and it does look like they're heading in that direction, then maybe using electricity for these processes will make sense, but for the moment it seems mostly to be reserved for these niche processes where electricity is basically being used because you don't want chemical contamination, so you can't burn fuel for heat. These are things like the semiconductor industry, where you're melting silicon to do this precision electrical engineering to make chips and so on. There they will use electric heat in industry. Other cases might be where you can design furnaces that are more efficient to do a particular job using electricity. And this happens to be the case where you're making aluminium. so that the efficiency savings help to make up for the higher price of the high-grade electrical energy compared to low-grade heat energy. Another point to make for these industries is that a large fraction of the cost of production goes to providing that heat. I looked up some costs for steel production. A quarter of that can go on the coal input. Because the profit margins are so narrow, and the input energy is such a big fraction of the cost, these industries are often already very energy efficient as a way of cutting costs. After all, if you can reduce by half the amount of coal you're using in your steel-fired power plant, then you've just saved an eighth of your overall budget and you'll be making more money than anyone else. This is less true in buildings, where most people aren't incentivised to ruthlessly optimise their home or office for energy efficiency, and for many people and businesses the energy bills aren't a major concern that they would invest in. But this in turn, the fact that these industries have had so many years to optimise and try and reduce the amount of fuel that they need to input into their business, that means that there aren't a lot of easy emissions reductions to be gained simply by using the heat more efficiently in the industrial processes themselves. In the long run, then, we need to switch as rapidly as possible to the low-carbon solutions that are available and being developed. But the very least we can do in situations where fossil fuels are still being burned to provide this initial energy is to make sure that we're not wasting the energy that they provide. If you're going to be optimistic about it, the fact that the free market has enabled some pretty great technological development to make these processes more efficient, because it's a key factor in running a profit, is evidence that actually, when the incentive is there, a lot of these problems can indeed be solved. Take Dow Chemical for an example. They made their chemical processes 38% more efficient between 1990 and 2005. That was an investment of $1 billion, and they saved $9.4 billion as a result from these efficiency processes. It won't surprise you to note that the best developments in industrial energy efficiency occurred when the price of fossil fuels was at its highest, and therefore you could argue that our systems, which emphasise profit at all costs, were actually emphasising efficiency a lot more because of how high the price of fossil fuels was. So the point is that a lot of these improvements can get made very, very rapidly when the industry, armed with big R&D budgets, a lot of motivation, and the greatest concentration of people and engineers who know the intimate details of solving that problem, can get in on it. There are people who'll say that really all you need to do is to mandate that companies reduce their emissions by 10, 15, 20%, etc., and that they will then develop the best technologies to do it themselves, in a far more effective way than, say, government-funded research in a university lab can do, which can struggle to make it to commercial competitiveness sometimes, even if it is ingenious. I have sympathy for both perspectives here, but unless you actually set up these incentives in these regulations, these things aren't going to happen. So having established what a thorny problem for decarbonisation heavy industry is, let's talk a little bit about the energy efficiency solutions that are suggested that might help here. Broadly speaking, Lovins points to 4 different types of step you can take. The first is reducing the amount of energy that's actually required to complete these fundamental processes and reactions. For example, often when you're undergoing complex chemical processes, the yield might be only 2 to 20% of the total possible yield based on the initial reactants that you had. For complex pharmaceutical products, it can be as low as 1%. So it's like saying, imagine you had enough carbon and oxygen to make 100 tons of CO2, but because of the complexities of the reaction, you're only making 1 ton. And this is simply because of the tricky nature of many of these reactions. If the pressure, temperature, or timing is a little bit off, other reactions occur that you don't want, which create undesired byproducts. Often the thing that you're trying to produce is only produced in small trace amounts in normal thermodynamic conditions. So one way of being more efficient is switching to so-called microreactors, where the conditions in terms of pressure, temperature, and reactant concentration can be managed more precisely. This way you need less energy to get the same amount of product, and you also need less reactants too. Depending on the reaction you're trying to complete, it can actually be cheaper to have hundreds of these microreactors rather than one large one, and it's definitely more energy efficient to do it. Another major thing you can do is to reduce losses in the distribution of energy around a facility. This can actually be something as simple as changing something like the layout of pipes that you have in your factory. I mean, when would you think of that as being a solution to climate change? But currently, where you have multiple feeds into the same pipe, we typically plumb them in at right angles. And that creates substantial friction compared to straight pipes that feed in at acute angles. Singaporean engineer Eng Lok Lee and protege Peter Rumsey run around redesigning various pipe networks, reducing the energy required to pump the fluids by 60 to 70%, using less pipes and therefore at less cost. A second example might be copper wires. Now, as you probably remember if you did electronics in high school, the wider the cross-sectional area of the wire, the less the electrical resistance, and consequently the fewer losses in electricity along the wire itself. Before the 1990s, the width of these wires was set mostly by a desire to avoid fires and prevent the wire from heating up too much. So you made the wire just wide enough to ensure that it wouldn't heat up and catch fire. But in both cases, you can see that people designing wires and pipes they're more concerned with minimising the use of initial material in constructing the device to save on initial costs, without considering the long-term savings that you can get with a more efficient system that uses more materials. And indeed, if you had a thicker copper wire, it would have less resistance and you'd have less loss of energy in your system. A third way in which you can hope to save energy in industry is basically just in improved designs for motors, boilers, pumps, fans, all of these common components that are common to lots of different industries and do use lots of energy. And the fourth pillar is putting wasted industrial energy to use. The irony is pretty obvious that we're talking about how much waste heat is being produced by industrial plants. Now, thanks to the second law of thermodynamics, it's really hard to avoid that. You're going to find it very difficult to prevent some of the work that you do from turning into heat for all of the reasons we've discussed. And yet, while we're producing all this waste heat in industry, we're also struggling to find the green alternatives for heating homes and businesses in the winter, and finding ways to heat up water to spin turbines, which is the whole way that we generate electricity. Similarly, when we generate power in fossil fuel power plants, only around a third of the energy can actually be converted to electricity, with the rest ending up as waste heat. So this is the principle behind combined heat in power plants. Don't do something silly like convert a fossil fuel to electricity and then use that electricity to run a radiator. Just deliver the heat straight to the person's home if you can. And in combined heat and power plants, you use the waste heat from generating power for heating in industry, or you use it to generate electrical power in the case of waste heat from industrial processes, and in all these cases you can substantially reduce the waste of energy involved. According to Lovins, if you tripled the combined heat and power capacity in the US, that alone would reduce its emissions by up to 12%, and low temperature heat from industrial plants could be sold to factories or buildings nearby, which again, he thinks in optimistic projections, could save as much as 10% of the US's industrial energy input. People often also look for thermoelectric devices. These are things that generate electricity from heat that would ordinarily be wasted. So you're probably aware of things like this that are being used in car brakes, for example, to regain some of the kinetic energy that you get when you're braking your car to charge a battery. Again, if you have such a system set up, you can typically reduce the environmental footprint of whatever operation you're engaging in other ways. For example, many pulp and paper mills will often generate their own power from all of the waste biomass in the wood that's being used to create paper, which obviously reduces the sheer amount of energy they need to input to the factory and deals with the waste problem from all of that pulped biomass when they're making paper. The point to appreciate here is that many complex industrial processes, actually, they're much like the car, where we described that you have this car in the first episode, where actually only a tiny fraction of the initial energy in the fuel goes into doing the useful task that you're interested in, which is shifting the person within the car. And you need to look for ways in your process, and every step along the way of the process, you're losing some fraction of the initial energy. Consider the energy life cycle of the energy that's used in a data center. First, you might have 100 watts of heat from fossil fuels that go into a power plant. The power plant promptly loses 2/3 of that as heat. Then, in transmitting the electricity that it generates, we lose 10%. Then, in cooling down the computers, we lose 33%. We lose another 4% on lighting the building. We use another 15% keeping the power supply permanent and uninterrupted. We lose 10% on the fans, 35% on the power supply. Depending on when the data center is operating, we could lose up to 85% on underutilization, that is to say that the load on the data center is not always there, so we're losing energy because it's being wasted to keep machines on that are idle. You can lose 40%, then you're running inefficient, bloated or unnecessary code. You've got computer processes running that don't need to be running or that are too complicated because people aren't thinking about how to make them efficient. So ultimately, you have that 100 watt input, and in this scenario, only 0.4 watts of that power is actually going into serving the useful, desired process purpose. Now, we can no more use 100% of that power as we can use 100% of our brains in that silly meme that people insist on spreading all the time. There's always going to be some loss in each step of the chain. That's just how these things work. But the point is, if you make efficiency savings at every step along that process, then they can easily compound. There are 9 steps in that chain. If you reduce the losses by just 10% at each step, this corresponds to an overall reduction in the initial power that you need of 60%. So that initial 100 watts to produce 0.4 watts of useful output becomes 40 watts. Put another way, if you can just save 10% of efficiency at each step in the chain, then you can do 2.5 times as much with the same input power. So again, the point here is that because so little of what you're actually putting in goes into the final endpoint in these complex processes, these small sounding efficiency savings stack up, they multiply together. And when you multiply a few of them together in a much better overall designed and integrated system, then you end up with some quite substantial savings and much less energy input that you need at the start. And again, we talk about fossil fuels and we talk about CO2 here, but even if you're imagining that we have a world where everything runs on electricity and it all runs on renewables, you're still going to need materials to make those renewables. You're still going to need extractive industries to make those solar panels and batteries and all this sort of thing. So regardless of how your energy system works, you are going to want it to be as resource efficient as possible. That just makes sense. This is a much more speculative point, and so it's a lot harder for us to quantify the effects it might have. But one tantalising prospect is the idea of getting more efficient industrial processes through biomimicry. Spiders can famously produce silk with a higher tensile strength than steel, and they obviously don't need blast furnaces to heat up to thousands of degrees Celsius to do it. It should be obvious to us that nature, with billions of years of trial and error evolutionary design, has been capable of producing things we can't even begin to match with our techniques in a lot of areas. Your own remarkable brain and body are evidence enough of this. After all, when you think about it, continuing to be alive as a human requires a daily input of energy from food that's around 8,400 kilojoules. That means that running you, your brain, your thoughts, your body, your immune system, your eyes, ears, nose, mouth, etc., everything, running you requires around 100 watts of raw input power. You can run an entire life on a similar amount of energy as is required to light up a couple of bulbs. That's quite an achievement of energy efficiency, don't you think? And it comes from the natural world. So things like biomimicry could potentially allow us to change the materials we use and the processes by which they're constructed to become much more efficient. Similarly, things like 3D printing are starting to come in, which can allow you to potentially substantially reduce material waste. Again, rather than having a block of material which is carved up and the scraps thrown away, we can manufacture things in exactly the right shape. One concept that repeatedly comes up in Lovins's book is the idea of integrative design. In other words, typically when you're designing some component to a building, whether it's the windows, the pipes, the wiring, the appliances, whatever it may be, then the design for this individual component is essentially considered and optimized by itself. You're not thinking about how the wire is going to work in the context of the factory, you're just thinking about making the best wire you can. So an example of this might be passive solar buildings where the windows, doors and walls aren't designed to be good windows, doors and walls only, but to absorb heat from the sun in the winter, thus contributing to the overall heating and air conditioning of the building. Another example might be, rather than having one unit that heats your building, another that cools it, and a whole bunch of appliances that produce waste heat which you then have to cancel out with your cooling device, storing that waste heat in a way that can make it useful. And similar ideas can of course be applied to vehicles as well. Rather than having separate designs for the body, the powertrain, the engine, the windows, the heating system, etc., you have a single component that serves multiple functions when considered in a more integrated way. When you have these individual components working together, you can achieve more than the sum of their parts in terms of energy efficiency. Lovins might be evangelical about integrative design, and it's clear that there are often some pretty good efficiency prospects you can get when you consider how to reduce the overall energy use of the whole system you're considering. And when we talk about whole systems, we could talk even about a town, a city. That's the idea of combined heat and power, to reduce the overall energy use of the whole city. But it's worth pointing out that this goes against the grain of how we do things at the moment, which tend to be focused on cheap solutions. This means mass-producing modular components that don't necessarily work all that well together, and having a high degree of specialisation in different components to a system that's being created. Because we have so much specialisation, because people are all in their little niches focusing on the one thing that they can do really, really well and really efficiently, they're not necessarily thinking about how it fits into the bigger picture. They're not even given latitude to do that often. So to harness this kind of benefit, you need to re-establish communications between people who are typically in charge of different parts of the design. It's not going to surprise you to hear, however, that the efficiency cornucopian view has its downsides. The issue being one of actual implementation. Lovins can happily calculate, for example, that if everyone used pipes that were fatter, shorter and straighter rather than thinner, lengthier and bendy, thus saving masses on the costs of pumping fluids around, we'd be able to save energy equivalent to half of the world's coal-fired electrical power generation. It makes sense. These pipes are another example of the end of a chain of energy use. If you imagine those Sankey diagrams, you might remember where all of that compounding wasted energy is flowing away from the original input. First you have the inefficiency in the power plant, then the wires to the factory, electrical conversion in the motor, efficiency of the pump, and then losses in friction in the pipes. Across all of this, maybe only 10% of the original input energy at the power plant is converted into useful kinetic energy pumping the fluid around. But if you can reduce that friction at the end point of use, you can result in much less fossil fuel needing to be burned at the power plant in the first place. Hence the arguments that if this were to be done everywhere, you could prevent millions of tons of fossil fuels from ever needing to be burned. This sounds like an amazing statistic, illustrating the huge potential of energy efficiency savings. But of course, to actually achieve things on this order of magnitude would require replacing every single pipe in the world. Which either means that Lovins has to successfully persuade everyone to replace their pipework with these designs, and then wait decades for them to get around to actually needing to replace the world's industry, or else we need to engage in a huge program of retrofits with a lot of initial capital allocated to them. In some cases, they may not even be possible. In Western countries, what's left is a lot of struggling manufacturing industries, using ageing plant equipment. These industries are very mature and growing slowly, if not shrinking. Any financial injection into these industries by government is often just trying to keep them afloat, rather than creating brand new plants or investing lots of capital in energy efficiency measures. For example, the EU in 2015 reported that since 2007 in the Great Recession, energy efficiency improvements slowed, just 1% a year as opposed to 2% before the crash, in the opposite direction to the kind of developments that cornucopians would want. They put this down to a lack of initial funding for new projects caused by the economic recession. Since the indication here is that global economic recessions make businesses less rather than more likely to invest in energy efficiency, which makes sense if you're struggling just to keep afloat, is not particularly good news for the post-COVID world, unless there are some major efforts to change that and focus on the benefits for energy efficiency. The shift away from fossil fuels in industry was also slow, even in climate-conscious Europe. In 2000, fossil fuels accounted for 65% of the energy mix in industry. In 2012, it was 56%, illustrating how difficult it is to shift to lower carbon alternatives. And in the countries where industry is expanding rapidly, there's likely to be an emphasis on rapid growth at all costs and not this kind of long-term efficiency saving or the environmental impact. So globally, you have a distribution of production that just doesn't really favour energy efficiency policies being taken up. Ultimately, it seems likely that there is a great deal of energy efficiency savings that can be made in heavy industries, and for those difficult to decarbonise sectors, it's going to be crucial to reduce the use of fossil fuels as much as we possibly can, because it may prove very difficult to do anything else and replace them entirely. If that's the case, in these industries, it increases the amount of CO2 emissions that need to be offset somehow, through negative emissions. If the expense of doing that was factored into the price of doing business for the emitting industries in general, you feel that they would find ways to save on the initial energy use. The issue is that if the only incentive is financial, and there are these high initial capital barriers to changing the way we do things, a lot of the most effective changes simply aren't going to be enacted, no matter how smart they may be, or how much sense it might make. In the next and final episode on this series, then, we will summarise some of the points surrounding energy efficiency policies, deal with the so-called rebound paradox, and try to make an overall assessment of just how important being more efficient with the way we use energy can be in our struggle against climate change. Thank you for listening to this Climate 201 episode from Physical Attraction. You can find us on the web at physicspodcast.com. There you will find the contact form. Any comments, questions, concerns, things you'd like to hear more of and less of, please let me know. I try and respond to all of the communications that come in through there. On Twitter, we're PhysicsPod. On Facebook, we're Physical Attraction. There are plenty of ways you can support the show. There's the PayPal link on physicspodcast.com and the Patreon, patreon.com/physicalattraction. There you will find access to lots of bonus episodes that only patrons get, and you will also find access for a very small fee to early editions of episodes that have not yet been released to everyone. And anything that you can do to support the show is really greatly appreciated. Thank you to the people who have subscribed already. Of course, you can also support us by telling as many people who might be interested to take a listen and reviewing us on whatever platform podcast you're listening to us at the moment. Now, our theme music, which I don't mention often enough, is by Melody Sheep, and you can check them out as well. They've done lots and lots of beautiful sciencey music over the years, so I do urge you to check them out. Until next time then, please do take care.